Hi, it's time for another math easy solution. We're going to discuss work and basically define it using integrals, and I'll go over an introduction into this field. Basically, the term work is used in everyday language to mean the total amount of effort required to perform a task. In physics, it has a technical meaning that depends on the idea of a force. Yeah, intuitively you can think of a force as describing a push or a pull of an object, for example a horizontal push of a book across a table, or the downward pull of Earth's gravity on a ball. And basically, in general, if an object moves along a straight line with position function s of t, yeah, for example, you have an object here and it's moving like this, but at different times you're going to be at different function or a different position here, and it depends on time. So this is s of t right here. Then the force on the object in the same direction is defined by Newton's second law of motion as the product of its mass and its acceleration. So force equals to mass times it by acceleration. So if this object has a mass and it's moving at an increasing its speed at an acceleration of a, then the force is m times a right here, and a in this case here is going to be the second derivative of this position function. So it's going to be m times s double prime of t of s right here, m times s double prime of t. And this is just equals to, in terms of writing in derivative format, goes like this: s of t dt squared. Yeah, and this is basically the formula for force. In the SI, or the Standard International Metric System units, the mass is measured in kilograms, the displacement, or the position there, in meters, or m, and the time is in seconds. So thus the force is going to be in newtons, which is force is defined in newtons, which is kilograms times meters per second squared. And you can just look at this function right here. So you're just timesing kilogram, timesing it by acceleration, meters per second squared right there. And this just equals to the Newton, or N. Thus, a force of 1 Newton acting on a 1 kilogram mass produces an acceleration of just 1 times just 1 meter per second squared right there. And in the US Customary system, the unit of force is the pound, or lb right here. This is a unit of force, and so it's not a mass. So if anyone tells you what's your mass, technically it's not going to be in pounds. That's going to be a force. And so this is it's not a mass, but it's a weight. So but it's a force. Or when someone says how much you weigh, it usually means what's your weight right here, which is a force. So and then in this case here, kilograms might not be that technically accurate. And so in the case of constant acceleration, the force F is also constant, and this force F is also constant, just because, well, if acceleration is constant, mass is going to be constant as well. So your force is, so then the overall force is constant, and the work done then is defined to be the product of the force times by the distance that the object moves. So W equals F times D, or work equals force times distance. And F is measured in newtons and D in meters. So if it's measured in then the unit for work is just the Newton meter, which is also known as the joule, or J. So joule equals to Newton meter, N times M right there. But if F is measured in pounds and D in feet, then the unit for work is just a foot-pound, which is about 1.36 joules in standard units. And now the above work equation, though, because we're dealing with a constant force, that's only defined for the force constant. But what happens if the force is variable? Well, let's suppose that the object moves along the x-axis in the positive direction from x equals a to x equals b, but at each point x between a and b, a force of x is acted upon the object, where f is a continuous function and not necessarily constant. So for example, if you have an object like this, you're moving it across here, but at each point it's going to have a different force on it. So if we were to draw this x and y axis like this, there's the x-axis, there's the y. So now this is at x equals a, this is at x equals to b right here, and we'll call this y equals f of x. So this is the force, and this is the graph of showing the force at every position x right here. So let's say it looks something like this, so it's not constant. So we'll just stick with this right here. So now the idea of finding the overall work done to push this, so we'll call this is y equals f of x. This is the force on the object. Well, this is going to be, when you look at this, this is a very similar to when we were basically dealing with areas under the curve and integrals. In fact, it's the same idea. So what we could do is break up this this region right here into sub-intervals. We'll draw rectangles like this. Let's draw it like that. So this will go up like this. So we keep drawing these rectangles across this path. And yeah, once you draw them all, you get something that looks like this. And the idea is we break this up into many rectangles, and now we could solve the force required to move the object, let's say from a general point right here, from this is x equals I, we'll call this at this point right here x equals I minus 1, and at this point in between is going to be, we'll call this a just a xi star. So just any point in between, this is where the function crosses right here. So now this is the region we're going to be dealing with. So the force required to move, I'll just type this out actually easier. So the force required to move the object from xi minus 1 to xi, so we're dragging it from here to here, and now we have a constant, this is a constant force up here, and this is just f of xi star. So that's what the star is. The star just means anywhere in between that we've decided to be where this rectangle's height's going to be. So basically the force required to move that's going to be, f equals to, we have that right here actually, f equals xi star, and now the work required is going to be this fxi star times it by this delta x. So in between here is a delta x. So assuming that these are all the same widths, we could sum up this. We could sum up this entire thing to find out the amount of work required to move it across. And again, this is an approximation because we have really wide rectangles right here. So this is a work I actually, yes. So that's work I required there. But now the total work, so work total, and then excluding the I there. So this is going to be, again, roughly equal to a summation I equals 1 up to n of xi star times by delta x. So this is again the same thing as our derivation for an area under the curve or an integral definition. Now if we were to break this up into even smaller and smaller rectangles and eventually go to infinity, the work required then is the total work. So and the approximation basically gets better and better as n gets larger, or delta x basically, that this will get smaller and smaller. Thus the work required to move the object is going to be from a to b. Well, I'll get to that in a bit. Basically, because we know this is a Riemann sum, so this will be equal to limit as n approaches infinity, so we're getting larger and larger. We put this summation down, which is a Riemann sum, which I've explained in my proof of the integral video, and you can watch that in the video link below. Delta x, this equals to, because it's a Riemann sum, convert it into a integral. So now this is going to be from a to b of f of x times by dx. So this delta x one is really, really small. That's just this dx, or infinitely small delta x. And now we don't need to the xi star, because as you get smaller, xi star will be basically equal to the both the endpoints xi or xi minus 1, or just x in general. So it's going to be one function. So this is our work formula, and now we've written it as a as an integral. So it's just going to be the area under the force curve, and which is just going to be the integral of the force from A to B. That's going to be your total work from A to B. Anyways, that's all for today. Hopefully you learned from this video. I'll go over some examples in later videos on work and integrals. And anyways, that's all for today. Hopefully you learned. Like always, you can download these exact notes in the link below. And thanks for watching. And stay tuned for another Math Easy solution.